So hello everyone, myself Sonia Rani. I welcome you on this third live session. So similar to last week, in today's session also we'll discuss some numerical problems based on the concept of the third week video lectures. So let's start the today's session. So let me take this pen. Okay. So the first question is here. What does the acronym of PECVD represent? So the correct answer for this question is your plasma enhanced chemical vapor deposition. So as you can see here, this PECVD stands for plasma enhanced chemical vapor deposition technique, PECVD. So let's have a look at how this technique works actually for the thin film depositions. So basically it consists of a chamber which have a substrate platen. So you can consider it like here. So this is suppose your substrate platen, this is your chamber, and this is your platen over which we can use the substrate, and here it has some inlet. So the basically the inlet will be the gas inlet. So whatever the gas we want to introduce in our this chamber, we can input that gas from this inlet. Now here as you can see, it also consists of a electrode here. So here it will be having a electrode, and that will be connected to a high voltage radio frequency, or simply you can say it is your RF power supply. Okay, so you can see the image here which is representing that how this PECVD technique actually works here. So this is my substrate platen, and I can keep my substrate here, or this wafer is actually representing the substrate, and this is your electrode which is giving you the RF power, and this is our inlet. The inlet is for the process gas, or we can call it as the source gas also, process or the source gas. So that will be entered into the chamber through this inlet. So PECVD is basically a technique which uses the plasma, as here the name is suggesting the plasma. So it uses plasma rather than the high temperature, for what? As an energy source. So in comparison to the other chemical vapor deposition technique, this PECVD technique uses this plasma as the source of energy. So as you can see here, this is the plasma that will be created between these electrodes. So what will happen? First of all, we will clean the chamber, or we can say first this is actually connected to a vacuum pump here. Okay, so until we get a value of pressure approximately equal to 1 millitorr. Once this will be completed, then we will introduce the process gas through this inlet. Introduce the process gas. Okay, So our process gas will be introduced inside the chamber throughout this inlet. Now in consisting this process gas, we can also include this inert gas depending upon the material we want to deposit. So this gas will be different. The third step will be, will apply a high voltage, at this electrode. Okay, so once this RF power supply will be applied on this electrode, so what will happen? It will causes the ionization of the gas molecule. Ionization of the gas molecules. So once this ionization will be, suppose this is your chamber, this is, here is your electrode somewhere, and this is your substrate platen like this, and here is the inlet also. So the pressure is around 1 millitorr here, and this plasma is created in this region. So the gas molecules are ionized now. So now what will happen? These ionized molecules will act as the catalyst, we can say, for the depositioning of the material which we want to deposit. So once this ionization will be happening here, so what will happen? Some chemical reaction will occur here, and following those chemical reaction, the material which we want to basically deposit on this substrate will get deposited on this substrate here. So based on the material we want to deposit, the process gas may be different. The process gas may differ depending upon the material. Okay, so as you can see here, the since the growth mechanism is continuous, and we can see that we can simply say the growth mechanism is continuous. So after some time, after running the process for some time, we can get the required thin film of the material. This is your running the process for some time. The thin film of the material will be deposited. So is it clear to everyone that how this PECVD technique works for the thin film deposition? You can write yes in the chat box. Is it clear? Okay. So, okay, great. So once this, I have deposited the thin film on my substrate. So now suppose that I want to stop the deposition. So anyone can tell me that what I have to do to stop this deposition now? So first let's recall that to start the deposition, first we created a vacuum of 1 millitorr inside the chamber. Then we introduce our process gas, or the source gas inside the chamber. Then a high voltage or basically a RF power supply is supplied, and due to that the ionization happens, ionization of gas molecules happen, and at last after some chemical reactions, the thin film of the required material is deposited. Okay, so this is the process for the to start the deposition. So what will be the case to stop the deposition? So what we'll do now? Anyone? Any idea? Okay, so once this is completed, say around I want to deposit 220 nanometer of the required film. So once this will be finished, so first of all I will stop the RF power supply. Yeah, means yes, Rupati. So first of all we will stop this RF power supply, and then also closes the gas inlet through which the gas was coming inside this chamber. So is it clear to everyone? Is it clear? Okay. So now let's move on to the next question. So here is your next question. The question is asking you the origin of the shunt resistance in a solar cell is what? Metallic contact, metal and semiconductor junction, crystallographic defect, or none of the above. So if I am saying about general consider a case of any device, if my input power is 100%, so my input is 100%, will my output will also be that 100%? No, for sure, correct. So in any device we are calling it as a solar cell, or in general we can take any other device also. So the input power is like if 100%, then output will not be your 100%, there will be some losses. So in case of the solar cell, now let's see a equivalent electrical circuit of a solar cell. So this is representing here a equivalent electrical circuit of a solar cell. It consists of, this is your light generated photocurrent source, this is a diode, and to represent some of the that how this actually this power is losing, this power loss is occurring here. So this will be here is shown in by the help of this series resistance and the shunt resistance, which is connected in series and parallel to this circuit. Okay, now let's have a look on this series resistance. Now just forget about this shunt resistance for this case. Now in the case of series resistance, now let's consider a simple PN junction solar cell. So suppose this is your PN junction solar cell, correct? Okay, so once the charge carriers will start moving to their respective electrodes, okay, whether they are moving here on the left hand side or whether they are moving on the right hand side, so there will be some resistance offered at the interfaces here, like here. So it can be due to your metal semiconductor junction, okay, and it can also be due to your this metallic contacts. Okay, so the resistance that is offered to the flow of the charge carriers, resistance offer to the flow of charge carriers, flow of charge carriers due to the metal semiconductor junction and the metallic contact, that is your series resistance, and that is denoted by capital R suffix S. Okay, now let's have a look at this shunt resistance. So basically in a solar cell, this shunt resistance causes the power loss in solar cells by it actually provides a alternating current path for the light generated current. Now for a solar cell, it can be due to the crystallographic defect, and also it can be due to the grain boundaries. Okay, now let's see. Suppose this is my some material and these are actually representing the grains of the material. Okay, so it is very clear that more the grain boundaries, we can say more path, more alternate path will be available for charge carriers to flow. So I can say that for a good solar cell, similar is the case of the defect, means more the defect, more will be the trap state, so more recombination will be occur in that particular solar cell. Correct. So for a solar cell we can say Rs should be minimum, or it must be your equivalent to 0, and Rsh, which is your shunt resistance, that is must be maximum, that is can be infinite for an ideal solar cell. Okay, but when we are talking about in case of, let's see, if my shunt resistance is very large, so if suppose the current is following this path from here, so if the value of resistance here is very large, so the current will not follow this path, it will go from this path, and that is actually good for the working of our solar cell. So we can write it like shunt resistance greater, or we can say that means we are having less defects or the less grain boundaries. So now see, what was the question? The origin of the shunt resistance in a solar cell. So we have seen that in case of the solar cell, there are two types of resistance. One is the series and the other is the shunt resistance. So for the series resistance, this metallic contact and the metal and semiconductor junctions are the main factors, and in case of the shunt resistance, the crystallographic defect and the grain boundaries are the main factors. So the correct answer for this question will be your option number 3. So is it clear to everyone? You can write yes in the chat box. Okay, what about others? Okay, so I think it is clear. So let's move on to the next question. So here is the next question. A solar cell under an illumination of 600 watt per meter square. So this is your intensity of the solar radiation. has a short circuit current value of 16.1 milliampere. So the short circuit current value is given here 16.1 milliampere, and an open circuit voltage VOC is also given, that is your 0.485 volt. So what are the short circuit current and the open circuit voltage when the light intensity is doubled? Okay. So we know that for a solar cell, the total current flowing through the solar cell is given by I equals to minus IPH plus I naught e raised to the power EV divided by eta KT minus 1. Okay, and let's have a look at the IV curve of a solar cell first. So this is my x-axis representing the voltage and the y-axis representing the current value. So my IV curve is something like this for a solar cell, correct? Now the voltage at this point is your VOC and the current at this point is your ISC, that is your short circuit current, and this is your open circuit voltage. So as you can see, at open circuit voltage the value of I is 0. So at V tends to VOC, the value of total current through a solar cell will be 0. So we can write it like 0 equals minus IPH plus I naught bracket e raised to the power EV divided by eta KT minus 1. This is clear to everyone? Is this clear? Okay. Now let's take this IPH, that is my photo generated current, on the left hand side. So we can write it like IPH is equals to I naught bracket e raised to the power EV divided by eta KT minus 1. Now we can write it like IPH divided by I naught equals e raised to the power EV divided by eta KT minus 1. And we can further reduce this expression like ln of IPH divided by I naught equivalent to EV divided by eta KT, and since my then 1 value is 0, so this expression, equation number 1, can be reduced to this value. And since we have taken this condition that I equals to 0, so V will be VOC, so we can further write this expression like VOC will be equal to eta KT divided by E ln of IPH divided by I naught. So is this clear? Okay. Just we call it as equation number 2. Now let's read the question again. So here they have given that if the intensity is 600 watt per meter square, then the corresponding short circuit current value is 16.1 milliampere and the open circuit voltage is your 0.485 volt. Now if the intensity of the light is doubled, so first we need to see that how this photo generated current or the current is actually related to the intensity. So this photo generated current is actually directly proportional to the intensity of light. How? So if the intensity of incident light increases, so what will happen? It will increase my number of charge carriers generated so the number of charge carriers generated will be increased. So this will in turn increase the current, or we can say it like the photo current through the solar cell. Okay, so IPH is directly proportional to the intensity of the solar cell, intensity of the sun radiation. So we can write it like IPH is equals to K, and we can write it like intensity, where K is your constant and N a constant. Okay, so now they have given that for an intensity value, that is your initial intensity, the value is 600 watt per meter square, and also the short circuit current value is 16.1 milliampere, right? Now if you see here, where for the condition of VOC the value of I0, but when we will talk about this point that is giving my short circuit current, here also you can see the value of V0. So when we will put this value of V0 in our equation number 1, we can get our IPH will be actually equal to I, and that is my I short circuit current. They have given that the intensity, that is your new intensity, is twice of the initial intensity. So the photo generated current at this will be we can calculate it like IPH1 divided by IPH2, that will be equal to K will be cut from both the expressions, and that will be my intensity, initial intensity divided by your final or the new intensity. And this is given that this new intensity is 2 times of the initial one, so we can write it like the photo generated current IPH2, that will be equal to 2 times of IPH1, and that is my value of ISC. So we can write the IPH2 will be 2 multiplied by 16.1 milliampere, and that will give me 32.2 milliampere. And since we are still talking about the short circuit current value, so this will basically be equivalent to the short circuit current value for the second case when the intensity is double. So out of these, you can see the only correct option which is giving you this answer is your option number 2. So that is 32.2 milliampere. So this will be the correct option for this question. Now let's also solve this expression for the case of VOC, in the case of how the VOC will be calculated. Okay. Okay. So we have obtained this expression of VOC. VOC equals to eta KT divided by E ln of IPH divided by I naught. So let's say if I'm talking about for this particular elimination, so we call it as VOC1, and this is my IPH1. So similarly, at this second elimination condition, we can write the expression of VOC like VOC2, that will be equal to eta KT by E, all are constant, and then ln of IPH2 divided by I naught. Okay, now the difference in this both two values will be my VOC2 minus VOC1, and that will give me since eta KT E divided by E all are constant, we can write it like this, and ln of IPH2 divided by I naught minus ln of IPH1 divided by I naught. Now we know a relation that we can write it like m minus ln n, that will be give me ln of m divided by n. Okay, so we can write this expression like eta kt divided by E ln of IPH2 and divided by IPH1. So is this clear to everyone up to this point? Is this clear? Okay. So this is my VOC2 minus VOC1. Now we can write it like VOC2 that we want to calculate, and VOC1 value is given. Okay. So just before we have calculated that IPH2 is 2 times of IPH1, right? So when we will put here, so we'll get this value and eta kT divided by E ln of 2. Okay. So when we will put all the values, this is Boltzmann constant, the temperature, eta value you can take 1, and E is the charge on the electron, that is 1.6 into 10 raised to the power minus 19, and the value of log 2, that is this 0.693, and this is your VOC1 that is given 0.485. Okay, so when you will put all the values here and after calculating, we will get the VOC2, that will be my 0.503 volt. So option number 2 is the correct answer. So is this clear? You can write yes in the chat box, and if someone is having any doubt, you can please ask. So Pankaj, here we have taken assume that this is your 1. Okay, so I think it is clear. So now let's move on to the next question. Okay, so the next question is that the room temperature under the forward bias, the voltage value is given through a PN junction and the current value is also given. So what will be the current value through the junction under the reverse bias condition? So we know that this expression for this reverse bias is given by I equals to not e raised to the power minus EV divided by eta kT. Correct. And we have this value, the value of the voltage is here 0.15 volt. T you can take it as 300 Kelvin, and also eta again 1, and the value of K, your Boltzmann constant, and this is your basically I naught, which is your 1.66 milliampere. So here the value is like this, e raised to the power minus 1.6 into 10 raised to the power minus 19 into 0.15 divided by eta, the value of K, and then the value of T. So it will, after calculating, it will give you the answer of 4 microampere. So it is just simply you have to put the all values here in this expression and you can get the current value under the reverse bias condition. Okay. So now let's move on to the next question. So the next question is, the solar radiation that is received after it changes its direction due to its reflection and scattering in the atmosphere is called the diffused, direct, or the beam reaction, or the beam radiation, sorry. So you can try this question, I think. What will be the correct answer for this question? It will be your diffuse radiation, direct, or the beam radiation. Okay, so let's have a look at this image. So suppose that this is your sun and this is your land, and this solar radiation are coming. So this will be, I think, more visible. Okay, so the solar radiation are coming from the sun. Okay, so there will be some radiation that will actually directly fall on the surface, like this one, that will directly fall on the surface of the earth without any bending or without any scattering through facing through a scattering through the atmosphere. So that will be my actually direct radiation. Okay, some will be like radiation comes, then it gets reflected from the earth's surface and then again moves into the atmosphere. So that will be my reflected radiation. And some will be like, since they in the atmosphere that consists of clouds, the gas molecules, and also some dust particles which are present and which are mainly responsible for the scattering of light in the atmosphere, scattering of light in the atmosphere. So after facing all this, the radiation that will come onto the surface of the earth, that will be my diffuse radiation. Okay, so we can call it like beam radiation and direct radiation are the same thing actually, and the radiation that comes, or that are the radiation that are received after the reflection and the scattering both, that are called my diffuse radiation. Diffuse radiation. So the correct answer for this question will be your option number 1. Is it clear? You can write yes in the chat box. Is this clear to everyone? Okay. So now let's move on to the next question. So the next question is, a solar module is what? It's like a newly installed solar cell, or it's something the series parallel arrangement of solar cell, or it is a series of solar cell when not used for the power generation. And the last option is none of the above. So what do you think? Which option will be the correct answer? Students, I think it's not that much difficult question. All of you can give a try. Yes, I will. If you have any doubt, you can please unmute yourself. Or you can write your doubt in the chat box also. That will also be okay. Pankaj is saying option number B. Others? Drupati also saying the option number B. Okay, so let's have a look at this picture. As you can see that here, it is basically something which you can see, it's all are the solar cells that are connected in both series like this and like this, and in parallel also. So a solar module is something which is connected in series or parallel arrangement. Okay, so the option number 2 will be the correct answer for this question. So good, Pankaj and Tripati. Sorry, Tripti. Okay. So now let's move on to the next question. Okay, so the question is, consider a pure intrinsic silicon crystal. The crystal is pure intrinsic. Okay, and the question is, what would be its intrinsic conductivity at 300 Kelvin? So it is asking you the conductivity, which is denoted by sigma, and what will be the electron and the hole concentration in a n-type. And a n-type silicon crystal that has been doped with 10 raised to the power 16 per centimeter cube phosphorus donors. Okay. So now the expression for the conductivity is given by Ne mu. The general expression is like this. Okay, so let's write first what we are given. So the temperature is given here, that is your 300 Kelvin. Okay, and you need to calculate the electron and the hole concentration. What will be the value? Here they have given the donor concentration, that is your phosphorus, that is 10 raised to the power 16 per centimeter cube. Okay, so this much amount of information we are having. So let's start. One more thing is that they are given that is your pure intrinsic silicon crystal, and we know that for a intrinsic material, we can write it like intrinsic silicon crystal, the value of Ni, that is your intrinsic charge carrier concentration. Charge carrier concentration is 1.5 into 10 raised to the power 10 centimeter per centimeter cube. Okay. Now when we are talking about the intrinsic conductivity, so we can write it like sigma I, and that will be equal to my Ni multiplied by E, and for the mobility we will consider the mobility of both electrons and the holes, right? So my value of sigma, this Ni is 1.5 into 10 raised to the power 10, charge on electron 1.6 into 10 raised to the power minus 19, and also one more thing, that mu is, you can take 1480 centimeter square volt inverse second inverse, and mu whole, that is your 490 centimeter square volt inverse second inverse. Okay, so when you will put all the values here, this is your 1480 plus 490. Okay, like this. So you will get your 3.1 into 10 raised to the power minus 6 ohm inverse centimeter inverse, and if I want to write in terms of meter, we can write it like 3.1 into 10 raised to the power minus 4 ohm inverse meter inverse. Okay, so this is the what, this is the conductivity, intrinsic conductivity, sigma I. Now another thing we have to calculate is the hole and the electron concentration. Okay, so for an n-type semiconductor, for an n-type silicon crystal, we are saying the most important law that we should know is the law of mass action. Law of mass action, and what is said that n of electron and n of p is equal to ni square, where your n is the electron concentration in a particular type of crystal, and np is your hole concentration, and this is again your intrinsic charge carrier concentration. Okay, now we can see that Nd, that is our donor atom concentration, is that is 10 raised to the power 16, and that is greater than our intrinsic charge carrier concentration, and this is around our 10 raised to the power 10 per centimeter cube. Okay, so now for this case we can write the concentration of the electrons in this n-type silicon crystal will be equivalent to Nd, and that is my 10 raised to the power 16 centimeter minus 3. Okay, now put this value in this equation. Now let's say this is our equation number 1. When we will put this value in equation number 1, that will give me that 10 raised to the power, just a second, 10 raised to the power 16 multiplied by the concentration of the holes, and that will be equal to the square of intrinsic charge carrier concentration, and that is my 1.5 into 10 to the power 10 whole square. So now from here we can calculate that it will give me 2.25 into 10 raised to the power 20 and divided by 10 raised to the power 16, and that will be 2.25 into 10 raised to the power 4 per centimeter cube. And in terms of power we can write it like 10 raised to the power 4 centimeter minus cube. That will be my whole concentration in this n-type silicon crystal. So this is your electron concentration 10 to the power 16, and this is your whole concentration. Now let's check which option is correct. So the donor concentration or the whole concentration is 10 to the power 16 per centimeter cube, and also the whole concentration is 10 to the power 4 per centimeter cube. So option number 1 will be the correct option for this question. Is this clear to everyone? Okay. So now let's go to our last question. So it is asking you that the total current through an illuminated solar cell will be what value? So we have already seen the equivalent circuit of a solar cell, and there we know that it is connected through a light generated or the photo generated current source, and also the diode here, and in here we have this shunt resistance, that is RSH, and the series resistance, that is our RS. So plus minus will be the voltage here. Okay, so the contribution will be due to the under the dark condition, or the current will be equal to the diode current, and we know that is given by I equals to I naught e raised to the power EV divided by eta kt minus 1, correct? And also when the light will be illuminated on this particular solar cell, so that will also have the contribution from the charge carrier generated, or the generated charge carrier. So that will be my IPH, the photo generated current. And since we are taking this output from the solar cell, so that will be in the negative sign, that will be with negative sign. So the correct expression for this total current through an illuminated solar cell will be your I equals to minus IPH plus I naught e raised to the power EV divided by eta kt minus 1. So option number 3 is the correct answer for this question. Okay, so thank you everyone. This is all for the today's session. So this video will also be get uploaded on the YouTube, and if you have any doubt regarding any question, then you can please comment on the YouTube video, and we will meet again on the next Saturday. And till then, have a good day. Bye.